Thank you for joining us today for this episode of the ATA Technical Webinar Series. Today's webinar is Understanding Aircraft Flutter and Predicting It with Simcenter 3D and Nastran, presented by Dr. Anthony Ricciardi. Before I turn things over to Anthony, I am going to give a quick introduction to ATA Engineering and who we are. So ATA Engineering is an employee-owned small business with a full-time staff of almost 200 at this point, over 200 if we include all of our interns and co-ops. And the majority of us are degreed engineers. We are subject matter experts that have been recognized by the National Academy of Engineering, Society of Experimental Mechanics, AIAA, ASME, and many more. We are also a classified U.S. government defense contractor and provider of engineering services as well as software. We serve a number of industries at ATA. Aerospace and defense are the principal ones, but we also have a very successful business in themed entertainment. Think roller coasters and other types of theme park attractions, but also industrial mining and equipment, consumer products, robotics and controls, and many others. We provide our services from our offices across the US. Our headquarters is in San Diego, California, but we have satellite offices in Los Angeles, the Bay Area, Denver, Albuquerque, Huntsville, Alabama, and Washington, DC. And from these offices, we serve customers with design, analysis, and test solutions for our customers' most challenging technical problems. ATA is also a Siemens Platinum level value-added reseller selling a variety of engineering solutions from Siemens, including those we're going to be talking about today, Siemens Simcenter 3D and Siemens Simcenter Nastran. We provide a number of services related to the software. We not only provide licenses as a value-added reseller, but we provide training, and in fact, ATA are the authors of Siemens Nastran training materials. So when you go to a Siemens Nastran class, you might not be surprised to find that the class is being held in Herndon, Virginia, or San Diego, California, because those are ATA locations and ATA instructors. But even if your training is taking place somewhere else, your training materials have been created by ATA engineers, just like Anthony Ricciardi, our speaker today. We provide our customers hotline support. We help implement software and also integrate software with any of our customers' existing solutions. The principal products that we sell and support are NX, Nastran, FEMAT, Star CCM Plus, Simcenter 1D, Simcenter 3D, and Teamcenter. For more information on software products, you can visit us at ata-plmsoftware.com, where you can download a number of different resources, including this master guide on Simcenter 3D, which is really a very deep technical product for engineers that not only handles structures, statics, dynamics, vibration, dynamic response, and all of the normal structural fields, but also such things as electromagnetics, etc. So for the master guide on everything that Simcenter 3D can do, visit us here at ata-plmsoftware.com. Today's speaker is Dr. Anthony Ricciardi. He is one of our Nastran instructors, but also an expert in fluid structure interaction, the calculation of flutter and similar aeroelastic phenomena. I'll now turn things over to Anthony. Anthony, take it away.
Thanks, Scott. Thanks, everyone, for coming. So Scott already introduced the topic and he introduced me. So we'll get into the content here. Let's start with the video. I think we can all appreciate what we're going to be getting into today. So this was think we can all agree, a horrible event. Fortunately, no one died. But if you look at the left wing, you can see the initiation of an oscillation that results in catastrophic failure of the aircraft. So I want to talk to you a little bit about understanding this phenomenon of aircraft flutter. And so we'll go over that. That'll be the first portion of this presentation today. We'll start by busting the myth that this type of response is a forced response, and that'll set us off on the right foot to understand what's going on, understanding the energy pathways that lead to this instability, and talk about the classical approaches for analyzing and predicting this type of response. And then we'll get into the specifics of using Simcenter 3D and Nastran to evaluate flutter for real world problems. A lot of times the situation that I find myself in is a customer will have a dynamics finite element model and they'll need to look at flutter. And so at that point, what commonly needs to be done is I need to create an aeroelastic model from an existing finite element model. So I'll show an example doing that, implementing a Nastran Flutter solution with pre and post processing using Simcenter 3D. I'm going to show some conceptual slides and a few equations, but we're going to mostly be covering these topics on the surface. So anyone with an undergraduate level understanding of mechanical vibrations should be able to follow the slides. I'm going to do my best to get you some useful information quickly. And so this is a rich topic, but I want to get you some useful information and get you out of here. So I'm going to do my best to do that. I had to make a few trade-offs on the content to make that happen. And so hopefully this will be worth your time, and I hope you get something useful out of it. So we'll get into the first section here. If you're not familiar with Flutter and you're new to this topic, you might understandably have the impression that Flutter is a forced response. And I'm going to tell you why it's not. So this is on the top of the slide here, the structural dynamic equation of motion. This is an ODE that's representing a discretized PDE. For example, if we use finite elements, we get a mass matrix, a damping matrix, and a stiffness matrix, and we have some unknown accelerations, velocities, and displacements. And these can be any coordinate you want: nodal displacements, rotations. It could be modal. Doesn't matter for the discussion. And this is the homogeneous form of this equation that we would use for an unforced response. If you were, for example, looking at the normal modes of a structure, this is the equation that you would solve. And typically we'd ignore the damping for that calculation, but you can include it if you wanted to. And for dynamic responses, on the right-hand side, there's a force. So this is the non-homogeneous form of the equation. So in the case of aeroelasticity, we want to consider aerodynamics. And this is a coupled system. So we have to write the aerodynamic force as a function of our structural response. And in doing so, we're writing the aerodynamic force in terms of the same unknowns as our structure. And in this case, I'm showing the aerodynamic force written in a transient form. This is difficult to calculate in this exact form, and so we often don't. We use an alternative form that we'll get into a little bit later. But in either case, the point that I'm making here is that when we write the aerodynamic force, that force has to be a function of the same unknowns as our structure, so that we have a coupled system. And when we do this, we don't have a special forced response form of the original differential equation. We have a new differential equation. And it's a homogeneous differential equation. And because of that, we want to find homogeneous solutions to this equation and determine whether or not those solutions are stable or unstable. So in reality, Flutter is a homogeneous response, and it's of a different differential equation than you might think going into the problem. So in that sense, it's not different than any other dynamic system that you might consider for stability. You might remember from your mechanical vibrations class, if you took one, that you can look at stability of fixed points for any system by looking at the eigenvalues and eigenvectors, which form the general homogeneous solutions for that system. So calculate the eigenvalues and eigenvectors and consider complex eigenvalue parts. So this is it's a quadratic system, and depending on the equations we have, we may get complex conjugate eigenvalues or real eigenvalues. And in either case, the real part of that complex or real eigenvalue tells us whether or not that homogeneous solution is stable or not. And the imaginary part tells us the frequency if it's a dynamic mode. So let's look at this case notionally, where we have a non-zero initial condition for a static mode. And as you'd expect, if you remember, the real part of the eigenvalue shows the stability. So if you have a negative real component, the mode will dissipate. If the real part is zero, it's a neutrally stable mode. And then if the real part is positive, it's unstable. Similar for dynamic case, except there's a non-zero imaginary part of the eigenvalue, and there's oscillation, but the stability is still determined by the sign of the real part of the eigenvalue. So in general terms, an unstable static mode, we call it static instability, and aeroelasticity, we call that divergence. It's a noun. And a dynamic instability, in general terms, is what in aeroelasticity we call flutter. So that's really the connection that I want you to have to stability analysis for general dynamic systems. So to get a little bit more into the details, I prepared this simple 2D section example. I've modified this from Hodges and Pierce book on Intro to Structural Dynamics and Aeroelasticity. And it's, as shown, a 2D airfoil section like you might see in a simple wind tunnel model that's fixed. There's an offset mass and inertia as shown. There's a linear and torsional spring. So it's a 2 degree of freedom model in terms of it has a pitch and plunge degree of freedom. I added a light viscous damper to this as well. And then I'm calculating the aerodynamic forces using what's known as Peter's aerodynamic theory. It's a transient theory. And to use that theory, I do have to add a few finite states to my equations. But what I have is a 2D transient aeroelastic model that we can use to explore the energy pathways that lead to the instability. And so to get there, we'll start by looking at the structural modes in vacuum. So this would be a typical normal modes analysis. It's a 2 degree of freedom structural model. We get 2 modes. So the first mode is a bending mode. And you can see that, there's some pitch up and pitch down coupling with bending that's due to the mass being offset from this axis, the axis where the stiffness is applied, which does impact the final result. And then the second mode is what I would describe as a torsion mode that you can see there. So this is a higher frequency mode. It's if we dimensionalize it, it could be something like 20 hertz versus 8 hertz. Hodges and Pierce use non-dimensional labels on a lot of their results. And so that's what I've done for these slides, where the frequency is written in terms of this other parameter, which is based on the uncoupled mode frequency. So if you don't like non-dimensional parameters, anywhere you see them, you can just think of it as a dimensional parameter. And I have labels, and if the units are a non-dimensional unit, it's implied that you know, even though the label may be velocity, it's a non-dimensional form of that. So those are the undamped modes for this structure. And let's think about the energy of this first mode. This is that same mode shape. And on the top right plot here, I'm showing strain energy and kinetic energy in the structure as time passes. So you'll notice is the total mechanical energy, or the sum of these, the strain and kinetic energy, is constant. And there's times where each is zero. And at that time, the other is at its maximum value, the total energy value. And in this case, if we ignore damping, this response does not dissipate. So this is what, you know, this in terms of energy, this is how I think about a normal mode. It's the frequency and shape, and this only happens at specific frequencies and specific shape pairs where the strain and kinetic energy are can pass back and forth between each other for an undamped mode like this. And one thing to note is strain and kinetic energy, oftentimes we can make reasonable assumptions that if we put energy in strain or energy in velocity of the structure, that at the time that that strain is released or that velocity is decreased, whatever is applying that force is recovering all of the energy that we put in. And in this case, it's going back and forth perfectly between strain and velocity in the structure. So if we now, oftentimes we ignore damping when we're calculating normal modes, but we know that there is dissipative structural damping in any real structure. And so in this case, I'm showing the mode including damping. And we see that the shape decreases over time as the energy dissipates. So we see that the total value, the sum of the strain and kinetic energy, is decreasing with time. And actually the value between the original total energy and whatever the current total energy is at any particular time is the area under this curve. Now, what's shown on this curve is the damping power. It's the rate at which the dissipative forces are removing energy from this structure. So this is an energy, and this is an energy rate. And recall, if we're looking at just the homogeneous structural equations, this is a general solution to that equation. And in the case of structures, it's always stable. You know, in aeroelasticity, we're interested in what's the impact of the fluid? What happens when we take this structure and we put it in, for example, a wind tunnel, and we blow air over the structure? You know, how is that going to change our situation? And we can evaluate that. We can pick a specific condition, say a velocity and altitude, and we can assemble our aeroelastic equations for that condition. So these matrices in this form will be a function of Mach number if compressibility effects are important, and they'll also be a function of dynamic pressure. And so we pick conditions, assemble these equations, and we solve these equations and determine the aeroelastic modes. And again, the eigenvalues will tell us information about whether or not the modes are stable, and as a result, whether or not our system is stable. And so we pick a condition, and then we plot, typically in aeroelasticity, plots that look like these on the right, where we'll have a frequency plot. This is two, frequencies corresponding to two eigenvalues, and the exponential decay rate corresponding to two eigenvalues. And we update our matrices for our conditions and look at the eigenvalues across different conditions. So I In this case, I'm looking in terms of velocity for example, for a fixed altitude, increment that, calculate my eigenvalues, plot them, increment, and then as a result, I get a series of solutions, and I can track my modal frequency and modal stability as I change my velocity. And remember that if the real part of the eigenvalue is positive, that's an indication that that mode is unstable. So this zero value, the zero line on this bottom plot, is the stability boundary. So this would represent a neutrally stable mode, and this is an unstable mode. The rest of the modes are stable. Now, another thing to pay attention to is, oftentimes I'll write this in terms of hertz, a frequency in hertz instead of angular frequency, and then the exponential decay rate parameter, which will often be referred to as damping in aeroelasticity. It's understood that it's referring to exponential decay rate, and the actual value may be adjusted so that it can be more easily compared to a structural damping value. And also, Nastran, for example, changes the dimensionalization depending on whether or not the mode is static or dynamic, as in if the frequency becomes zero, as in critically damped, or a mode that has damping, effective damping above critical damping, this definition will change. So we may see a discontinuity in the result because it's not the eigenvalue part directly being plotted. So that's a few pieces of information. We'll revisit that later. So we'll go through a similar process for our simple model here. On the left, you see the results for that model. So this is first and second mode frequencies changing as we change velocity, and the exponential growth or decay rate changing as velocity is changed. And I'm showing a circle for which mode shape and energy plots are being shown on the right. So this is the bending mode at this lower velocity. This is a reduced velocity value. You can multiply this by 60 if you want to think about this in terms of feet per second. And you can multiply this by 6 or so if you want to think about that in terms of hertz. And one thing you'll notice is that for this low velocity, the mode shape is pretty similar to the damped bending mode shape. So, a small amount of velocity, assuming that the mass of the air is small compared to the mass of the structure, the effect at low velocity will be very small. And then as you approach zero velocity, you'll approach the vibration mode frequencies is what you should expect for the frequency plot. And so we've increased the velocity a little bit. And so the mode shape has changed a little bit, and we've added a little bit of damping effectively because our exponential growth rate has decreased a little bit. And so let's look at what's happening here. So this is the same plot as before, where the strain and kinetic energy are plotted over time. And we can see the total energy is dissipating. And on this plot, we again have the viscous damping power. That's the rate at which viscous damping is removing energy from the structure. So on the negative side of this plot, that's energy being removed. And above zero on the positive side, that's energy being added to the structure. And additionally, we have the aerodynamic work, or the aerodynamic power, plotted versus time as well. And confusingly, probably for this very first slide, is they're very similar. The blue is the aerodynamic power, and it's mostly dissipative because it's mostly negative, although there are a few points in time where the aerodynamic power is positive, and that's going to change as we change the velocity. But effectively here, looks like we've about doubled the amount of damping, and we doubled the dissipation rate for this mode by blowing air over it at this velocity. So I'm going to click through. There's a few more modes, and we're just going to see how things progress. So this is for a higher velocity, the same mode. And we see that we have added significantly more dissipation because the aerodynamic power is very rapidly removing energy from our structure. And one shortcut I like to make sometimes is, even though it's a simplification, if we make temporarily the assumption that our aerodynamics are steady, where we only consider the contribution of lift from the pitch. One thing we know about a steady case is that, for positive pitch, we'd expect the lift to be in the positive direction. And for negative pitch, we'd expect the lift to be negative in the negative direction. And for very low reduced frequencies, it may approach the steady type result. But one sort of shortcut that you can get away with at times is think about that shortcut and think about what direction the aerodynamic force is in, and and compare that to the velocity. And if the aerodynamic force is opposing the velocity, that's removing energy from our structure. So let me try to get a screen capture here. So this is the peak velocity point for plunge. And we see that at that point that our aerodynamic power is at its peak, where it's removing energy from our structure. So as it's opposing the velocity due to the air blowing over this airfoil. So if this continues, we get more and more dissipation due to the aerodynamic forces until, in this case, it almost seems like we're approaching a critically damped or a value where it's almost above critical damping, where this almost is becoming a static mode. Eventually, we might see that. Although in this case, we don't quite reach that point based on what the plots show us. But we just incrementally increased the amount of energy that the aerodynamic forces are removing, and we see that our exponential growth rate, which is decay on the negative side, so our exponential decay rate is just getting higher and higher as we increase our velocity for this mode. Now we have our second mode, which is torsion mode, and we'll look at the same result for that mode. Similar results, we see, both positive and negative power produced by the aerodynamic forces, but overwhelmingly, when we combine these, this is a dissipative response for this velocity. So let's increment that further. We see some coupling of the plunge degree of freedom for this mode as we increase, and eventually we see a reversal in our trend, and we get to a point where we're at neutral stability. And when that happens is, if we look at the structural damping power and aerodynamic power, when we integrate both of these, if the area beneath the curve, or beneath zero for both of these curves, is equal to the area above zero, that's effectively zero aerodynamic work done per cycle. And so this is a neutrally stable mode. It's undamped effectively, and it just has the same total mechanical energy value as we, the per cycle anyway, the total energy is not decreasing with time. So this is the stability boundary for Flutter. If we go faster than this, we're going to see that the aerodynamics is doing more work, and that the area above zero in terms of the power curve is going to drive this mode unstable. And so that's what we're going to see here. This mode. We have a positive growth rate, and with each cycle, the mode amplitude increases, the total energy in our structure increases because the power done by the aerodynamic work is eclipsing the dissipative forces provided. So that's the background information. Hopefully that's maybe a different way to look at it than you may have seen previously. I hope that you followed that. You know, we've seen these this tool of plotting the eigenvalues that we're going to revisit using Nastran because the results are going to look similar in terms of how we'll evaluate them when we get there. So I'll get right into that. Again, what's going to be demonstrated here is we're going to start with a FEM that we already have, and we're going to create an aerodynamic model. We're going to create splines, which we'll talk about what those are used for, and we'll create the solution parameters we need to solve this. And I'll do a live demonstration here. The whole process will be implemented using Simcenter 3D. And for the aerodynamic model definition, Simcenter 3D provides pre-processing features specifically for doublet lattice method and subsonic wing body interference theory. There are additional methods available in Nastran. All of those methods are unsteady, and they all assume that the flow is inviscid and irrotational. So let me pull up Simcenter 3D here. I have a few part and FEM and sim files. So this is Simcenter 3D format simulation file and some supporting FEM file and part files. I'll just open that up. You could just as easily import a Nastran input file into Simcenter 3D if that's the format that you have. So this is a simple wing case that that we're going to have time to look at today. It's got some internal structure that's pretty standard, ribs and spars. Let me turn off the geometry here so you can see those features. And so this is going to work to represent our structural dynamics, and we're going to add what we need for Flutter. So we'll start with creating the aerodynamic panel model. I'm going to activate the FEM, and I'm going to make a change to the solver environment, changing the analysis type from structural to aeroelastic. And that's going to add some features that I can use for what I need. So under nodes and elements, I have options to create aerodynamic panels and aerodynamic bodies. So we're going to create aerodynamic panel. And this is all data corresponding to, if you're familiar with Flutter and Nastran, the C-Aero1 entry. And what Nastran needs is location of the leading edge for the span that we're defining here, and the chord lengths at those points. So this is 60 and 36 inches. The divisions on our chord, and there's some nice features in Simcenter 3D that allow you to specify how the chord wise boxes are going to be biased. So I'm going to pick cosine divisions, and you'll see how that looks when we show the result of this. So that's going to be 8 chord wise elements or boxes, and 24 span wise boxes. I think will work fine. And I'm just going to leave the defaults for the remaining inputs. I can click show result here, preview that. Not seeing that. Let me unhide it. So there it is. That's what was just created. It's a surface panel representing the aerodynamic shape of this wing. And so that's part of what we need for evaluating Flutter. And that's a pretty simple process, and it's a simple geometric representation. And so we've added that. So the next step is defining the spline. So right now we have two independent meshes where we have our structural dynamics mesh and we have an aerodynamic mesh, and we need to unify those. So splines are what allows us to do that. They create constraint matrices that make the aerodynamic degrees of freedom dependent on the structural degrees of freedom. And there's a few different types we can use. It depends on the situation. Today, we're going to use an infinite plate spline. It's a 2D spline, but there's some others that are available for you to use. And Simcenter 3D supports all of these, depending on your situation. So let me do that. What I'm going to do is activate the simulation. And then I'm going to create a Flutter solution. So it's going to be Simcenter Nastran solver analysis type. We're going to set to aeroelastic and solution type. So there's a few options for this. We're only covering Flutter today. So what we're going to look at is solution 145 aeroelastic Flutter, but there's also static and dynamic aeroelastic responses that are also supported by Simcenter 3D. So I'm going to create this Flutter solution. I'm going to accept these defaults for now. We're going to revisit some of these solution parameters later, but first we're going to make the spline. So under home and simulation objects, we can select aero spline. There's a few different types we can look at. Linear is a beam spline, or we can look at what in Simcenter 3D is categorized as a surface spline. We can pick our boxes that tell us which aerodynamic degrees of freedom are going to be dependent on this spline. So we pick the first and last box are sort of the leading edge of the root, and then the trailing edge of the tip are the box order that we need. And for the structure nodes, I'm going to use a group reference. And there's a group here, and you can see it. It's where these orange circles are when I have that group selected. And for this spline group, these are the structural nodes that will define the structural side of the spline on which all the aerodynamic degrees of freedom are going to be dependent. We don't want to use all of our structural nodes. We just need a subset. And it's useful to pick points where there's some stiffness. We don't want to pick the middle of a panel that may encounter some type of panel response in our modes. It's better to pick stiffer points where you have maybe the intersection of the rib and skin, or intersection of spar and skin, or all three, to give a nice harder points, you might call them, to avoid any panel modes in the response, unless you're specifically wanting to include that for some reason. So I'm happy with this set of nodes. I'm going to leave the default 0 linear attachment flexibility. I'm going to leave, so the spline fit, I'm going to use infinite plate spline today. These other types are really for more special cases. So this is going to be the most common, infinite plate spline, and we can also pick different splines for force and displacements. We'll use the same one for both. So we've created our spline, and there's this model entity that shows up that's visualizing that. And so that unifies our models so that we can move on to the Flutter analysis. But before we create those parameters, I want to make a few more, give you a little bit more information about what's going on in the background for solving these aeroelastic equations. So we've talked about, the fact that we're looking for homogeneous solutions to this equation. There's the typical process for doing that. But in this case, I've taken my aerodynamic and structure terms and I've separated them. And as we look at the aerodynamic terms, one thing that I want you to think about is that calculating unsteady aerodynamic terms is very difficult to do for a transient response, including arbitrary motion. And the reason that that's complicated is because if you have arbitrary motion, you get an arbitrary wake. There's vortex shedding that happens at the trailing edge, that's dependent on the motion. And capturing that for any motion is challenging, and it's something we can do. So, you have the option of dealing with it, calculating aerodynamic terms that are valid for arbitrary motion. And this involves including additional finite state degrees of freedom. And if you go through the trouble of doing that, then you can use a typical eigenvalue approach for the stability assessment. So in aeroelasticity, we call that typical approach P method. But it turns out that there's another option that is preferred most of the time. And that option is we restrict the aerodynamic terms to only represent harmonic motion. And that's something that requires specialized algorithms. We can't use the typical eigenvalue solution algorithm. We still want to find approximate eigenvalues, but we use specialized algorithms for doing that. So you may have heard of K method or PK method. Those are methods that allow us to do that. And this assumption is approximate anytime that we're not looking at a non-harmonic solution. So if the result is not neutrally damped, there's some additional error introduced by making this assumption, but it's still usually the preferred option. These specialized algorithms take a little bit more effort than the typical algorithm, but computing aerodynamics for this option one is more trouble than using the specialized algorithm. So because of that, option two is almost always the preferred option. And that's the option that's available in Nastran. And you're probably thinking that seems like a pretty big assumption. So I've added this slide to set you at ease a little bit. The error introduced by restricting the aerodynamic terms of harmonic motion is usually acceptable. And you have to think about, what we're looking for in these cases. This is the same results for that 2D section. But what I've done here is I've plotted the original result, which you've already seen, which is P method. I've used transient aerodynamics and the traditional eigenvalue approach. And then on top of that, I'm showing the result using PK method, which is the method that allows us to solve for the eigenvalues while restricting the aerodynamics to harmonic motion. And what we find is, as we should expect, the results are identical at the neutral stability points. But as we get away from those, we get an increase in the error introduced by how we're approaching this. But I would argue that the error is actually small and the results are useful at all of these points. And then particularly, the area that we're most interested in is near the boundary to the instability. And we get very good results there. So we get an exact result at what the neutral stability point is, or in terms of there's no difference between the two methods on the location of the neutral stability point and the slope, which we're often quite interested in at the neutral stability point. We get very good agreement at these solutions that are near zero. So that's why this is the typical approach. The benefits greatly outweigh the costs of approaching the problem this way, and that's why it's done this way most of the time. So to define our solution, we need to specify which points we want to look at. And there's a few different things we look at. What's our density, what Mach number and velocity we're at. In the case of PK method, we would specify velocity, or K method, we'd specify reduced frequency. And another thing to be aware of is density, Mach number, and velocity are not independent if we are considering our atmosphere. Density is dependent on altitude. Mach number is dependent on our velocity, and it's dependent on temperature, which is dependent on the altitude. And so there's really two independent variables for those three quantities if we want them to be consistent with the atmosphere. And we can pick points that are consistent. So we would call that a match point if we pick combinations of those that are atmosphere consistent. And Simcenter 3D includes a standard atmosphere model that can assist us in specifying those points, which is very convenient. And only K method really allows you to specify those points in this way. So PK method allows you to have a matched point solution. That's not an option with K method, just for your awareness. So we'll specify that information in Simcenter 3D. There's some additional information needed, reference quantities, aerodynamic symmetry conditions. And then the last thing we need is a set of Mach numbers and reduced frequencies. And reduced frequency is a non-dimensional form of frequency for the aerodynamic matrix calculations. PK method needs aerodynamic force matrices that are continuous functions of Mach number and reduced frequency. And so the way Nastran works is the user specifies a set of Mach numbers and reduced frequencies at which those matrices are calculated, and Nastran interpolates those matrices in between those points. So we just need to specify the points where they're going to be calculated, and that'll be the last thing we need before we run our analysis. So back to the model here. All that information we're going to specify in our Flutter solution. So we go to that here, open up our solution. Let's start in the bulk data section. And we see that in the bulk data section, we have aeroelastic analysis parameters. So let's open this up. So we have a few things we need to find here. Reference chord length, we pick a representative chord length for this. Pressure altitude. So this is one of those situations where really what we need to specify here is a reference density that will be used by the solver. But if we want to, we can specify this in terms of altitude and let Simcenter 3D calculate the reference density based on the standard atmosphere model that's built into Simcenter 3D. So to do that, you put the altitude in, then you click this calculate reference density from pressure altitude. I'm not used to this unit used for this reference density. So something I'm more used to would be kilograms per meter cubed or slugs per cubic foot. So let me have Simcenter 3 calculate that in terms of kilograms per meter cubed. And we see that this is a familiar number. And then of course, Simcenter 3D will convert this to consistent units that we've selected for our solver on output. The other thing we'll want to specify is our aerodynamic symmetry. So we have a plane of symmetry at the root here. That's going to be the XZ plane. So I'm going to specify a symmetry condition. We could also specify anti-symmetry. And then I'm going to pick no symmetry for the other plane. This dynamic analysis parameter is used for is not used for Flutter, so we're going to leave that blank. So we specified our aerodynamic parameters. We want to specify those points. So Mach number and reduced frequency tables, these are the points at which those aerodynamic matrices are going to be calculated and interpolated in between. So I can click create. And I give it a list of Mach numbers and reduced frequencies, and it'll create a pair for each of those. I'm going to run a constant Mach number analysis today. So I'm just going to put the one Mach number that I'm actually going to run, but you could put as many as you need. And I'm going to put a set of reduced frequencies here. These reduced frequencies, you want to be biased towards 0, and you want to go from a value near 0 to a value near roughly 5. So you can see the points I chose here. So this, again, this is where the aerodynamic matrices are going to be calculated. I can click add to add that. And then that part has been set up. Under case control, we're going to leave the defaults for a lot of this. Aerodynamic symmetry can be specified here or bulk data. We've already specified it in bulk data, so we're not going to specify it here. Before I forget, I'm going to put a 2% critical damping value here for the structure. And then I'm going to input some Flutter data here. So let's take a look at this plot. These aerodynamic Flutter data are specifying our solution points. So I've got a few options here. I have Flutter analysis method, K method, PK method, no looping, KE method. K and KE method are essentially the same method, but there's some different backend algorithmic implementations that are used for either PK method and PK method no looping, it's sort of the same story. We're going to pick PK method and then pick our results here. So it's a similar result where if we wanted to, we could pick pressure altitudes and have Nastran or have Simcenter 3D rather calculate the density ratios for us based on the standard atmosphere. But I'm just going to specify a single density ratio here. So I'm going to do a constant altitude analysis today. So, and this is the ratio. Show that again. This is the ratio between our reference density and the density that will be used for the analysis. So we've already specified our reference sea level density, and then this is a multiplier on that will be used. For Mach number, I'm just going to run Mach 0.8. And then for velocities, I'm going to give a range of velocities that I have a text file open in my other window. So I'm going to copy those. You just have to generate a list for whatever velocities you want. And this is really the part that's going to vary for the solution today. Nastran will calculate our eigenvalues at all these velocities, and then we'll look at the results for these. So that's the last thing I needed. I'm going to leave defaults for the rest of the inputs. And we should be ready to run this analysis. I'm going to save that. So I just have to hit solve. Okay. And this is going to be very fast. Got a solution monitor window up, and it's just showing some of the information from the FO6 file. Solution is complete. Okay, I can select this job monitor and click information. It'll print this report here. No errors or warnings found in the output file. So that's good news. So we've run our case. Let's see what we got. So I've activated the post-processing navigator here, and you can see we have this Flutter solution. Oh, okay. So I see that I have some zero frequency modes, which means that I forgot to specify my boundary condition. So this is easy to forget when you're creating new simulations. So you also want to make sure the spline has been defined, because there's these objects that are in the simulation navigator. This is the aero spline object. This is the constraint object. So I'm going to pull this constraint down so that that constraint is applied for this analysis. And I'm going to rerun the analysis. Okay, let's check the modes again. That's more like it. So we've got 3.5 hertz and 6.5 hertz roughly modes. These are the structural normal modes. As part of the solution process, Nastran does a normal mode solution and then transforms the degrees of freedom to modal degrees of freedom for the Flutter analysis. And one thing we want to do is we want to verify that our splines are satisfactory for what we need. And so what we want to do is we want to plot our structural mode shapes before we look at our Flutter stability results, which we have. We're just going to check this mode result, confirm that our splines have worked correctly. So I'm going to hide the skin, and underneath the skin, you can see the aerodynamic panels. And we're just going to confirm that the spline, which is making these aerodynamic panel degrees of freedom dependent on the structural response, hasn't introduced anything weird, and we're getting results that are consistent between the two meshes. And so we've got a good set, a good spline defined. And coincidentally, we haven't looked at the modes for this model yet, but you probably noticed that we've got sort of a bending mode here, and our second mode is more of a torsion mode. So we can keep that in mind as we open up our Flutter results. So for the Flutter results, we can go to this XY function navigator, and Simcenter 3D will read our eigenvalue, our complex eigenvalue results from our output 2 file, which Nastran created. And we can expand these. These are the frequency and damping results for all of our modes. So this is the damping result. The unit doesn't default to the useful form here, so we have to switch this plot over. And this is what previously we had looked at, the exponential decay rate plot. Let me zoom in. You can see a little bit better what's happening. If you remember, we track the real part of the eigenvalue and see how the mode is changing as we change our velocity. So what we find by looking at this, that we have one mode here that's going unstable, corresponding to the second mode. So that's something we're going to want to look into a little bit more. Let's look at the frequency results. So this is the frequency results and how they change as we change our velocity. We've got interesting result here. So this mode becomes, reaches critical damping and beyond, and becomes a static mode. And the rest remain dynamic modes over time. This is a bit busy, so let's just look at the first two modes. I'm going to replot these. I'm going to switch this to real only. And this is sort of analogous to what we were looking at previously. We've got eigenvalues changing as we change our velocity. We've got a mode that goes unstable. And in this case, we have mode that becomes static. So we can look a little bit more into what's happening here. This is our neutral stability point. Let's zoom in and just see what velocity this is occurring at. So this is about 4,900 inches per second. Let's take a look at what that mode shape looks like and evaluate that result. We'll do that in a minute. Let me go back to the full view here. Another thing you probably noticed is there's a giant discontinuity in our eigenvalue result. And the reason there's a discontinuity is because it's not actually an eigenvalue result. This eigenvalue has been modified, so it's converted into a damping unit, so it can be more easily compared to structural damping. And that definition changes when the mode becomes static. So something is not easy to follow in terms of the coloring here. We know that this red mode is the mode that is becoming static. So the colors are not exactly matching up. But what happens when this mode becomes static is the output definition for what this damping term is defined as actually changes. And so because of that, there's sort of a divide by omega term for these dynamic mode portions. And so you actually see it sort of asymptotically approach the value where this becomes static, and then the definition changes there. This hasn't become unstable yet. Another thing to note is that the mode can become static before it becomes unstable. You do have to wait for this result to become positive before the mode is actually unstable. So you can have a static mode that is stable or unstable, and we see that we're still below 0 here. So this is not yet a divergence mode, but if we increase the velocity, we would get to what we refer to as divergence, which is a static instability. All right, I'm running a little bit over here, so let's just take a look at that mode shape, and then we'll move on to questions. So if you do want to look at an aeroelastic mode shape, the way you do that, and this is the way Nastran input works, is in PK method, when you provide the velocity, you provide it as a negative velocity, and that triggers Nastran to compute the eigenvalues for that mode. So that's all we have to do. This will come. This is around where the neutral stability point is. So let's take a look at this, the eigenvalue corresponding to the modes at this velocity. I may have to clone this solution to get a new result. So all I've done is I've updated the velocity list to have one value, which is negative. And we're going to rerun it again. Okay, everything looks good. So we can go to our results here. So we got a list of modes again, but now we have a real and a complex option. So this is the structural mode, and this is output from the Flutter solver, which is the complex eigenvector corresponding to the velocity that we picked. And we can take a look at that. Now, since this mode is complex, you want to look at the animated mode shape, and that's something we can do. So I'm just going to go to this contour plots post view. Click edit post view. So I'm looking at complex mode 2. This is the contour result. I'd actually like to see the rotation. I'd like to see rotation in the pitch direction, which is Y. So I'll set that as the contour color. But then I want to deform this model and animate it. And I can pick complex options assigned amplitude. And this will let me animate this mode shape. And let me pick a modal style option here. I'm going to put a lot of frames and a short delay just so we get a smooth result here. This doesn't look quite right. Let me see what's going on there. May not like that I pick rotation. So let's pick the displacement. No, I picked the wrong option here. So at phase angle is the option that we want to get the complex mode animation right. That looks better. And what you'll see is we just look at this airflow cross section of this model is that we get a pretty similar result to what we saw for the 2D section. So there's a connection there. And again, we see this sort of response where if we make the assumption that would only be valid at basically zero reduced frequency, that the force is in phase with pitch, which we know that there's plunge rate terms and pitch rate terms that are affecting the kinematic angle of attack effectively, and then also shed vortices that change that. But just for the sake of a shortcut, we do find that for this type of result that we're getting pitch up as the velocity is increasing, or as the velocity is going up, and pitch down as the velocity is going down. And so this is consistent with aerodynamic force, if that's what's happening, which we found that we're at a neutral stability point here, that the aerodynamic forces are doing work on our structure, or at least doing enough work such that they're equal. They're at the point that they're overcoming the dissipative forces within the structure. And if we proceed past this velocity, it's going to get to a point where this mode will become unstable. So I'm going to stop there. We could talk about this all day, but I think I should just hand it over for questions at this point and see if anyone has any before the end of the meeting.
Very good. Thank you very much, Anthony. It's a very interesting presentation. I do apologize to the participants, but we have run so late that we're going to forgo the Q&A session today. But do feel free to contact me directly after the webinar if you have any specific questions. My name is Scott Tebow. I work here in our Huntsville, Alabama office. You can reach me at scott.tebow@ata-e.com, and I would be happy to pass your questions on to Dr. Ricciardi. Again, thank you all for joining us this afternoon for this webinar on understanding Flutter and calculating it with Simcenter 3D and Nastran. If you have any questions, or if you are interested in the Simcenter 3D and Nastran software and don't already have them, please feel free to reach out to us. We would be happy to hear from you.
Thanks, everyone.